Hi everyone, my name is Stefano Hermon. I'm an assistant professor at Stanford, and today I'm going to be talking about some of the work we've been doing on using machine learning and satellite images to better understand food production and agricultural system at a global scale. And this is based on joint work with many students, postdocs, and people at Sustain Lab at Stanford. As you probably know, food security is one of the biggest challenges our society is facing today. There is close to 1 billion people around the world that don't have enough to eat every day. And although there has been a lot of progress over the last few decades, the situation has actually been getting worse since 2015. And we don't know what's going to happen in the future. Things might get even worse because of climate change, natural disasters, unexpected things like the current pandemic will live on, export controls, and so forth. Now, what can we do to help as machine learning researchers? Well, one issue that people in this field often face is that they don't have good data to help them make better decisions. Using this very nice quote from Kofi Annan from his recent paper on food insecurity in Nature, he said, "Data gaps undermine our ability to target resources, develop policies, and track accountability. Without good data, we're flying blind. If you can see it, you can solve it." And in practice, what this means is that we often know about famines well too late, maybe years after a famine happened, when it's too late to actually be able to do something. People don't know what kind of policies or what kind of plans work, which ones don't. And generally, it's very hard to target aid, target resources, because it's very hard to get reliable, timely information about what's going on the ground. And so the idea is perhaps we can use machine learning and remote sensing data to come up with better ways to provide this sort of data in a more scalable and inexpensive way. And so the kind of like goal of many of the projects that we've been working on at Stanford is to figure out better, more scalable ways to provide timely, accurate data on food production, which can then be used as an input to better address food insecurity issues. If we can predict ahead of time that there's not going to be enough food production in a particular region of the world, perhaps because of droughts or locusts or natural disasters, then we can provide that information to organizations like the World Food Program, and they can use it to provide help at the right time. Now, why is this possible now? Why haven't people been doing it before? Well, there are kind of two reasons. The first one is that there's been a lot of progress in remote sensing technology. Maybe up to, let's say, 15, 20 years ago, people used to work a lot with data coming from Landsat sensors, and here the resolution is fairly low. You can see here an area in Uganda, and every pixel here corresponds to an area of 30 meters by 30 meters. So, you can get a sense of what's going on the ground, but the resolution is just not good enough. And but these days, it's easy to get access to much higher resolution imagery. This is from Planet. These are like 3 to 5 meter resolution, and you can get access to this kind of images pretty much everywhere in the world, and they are updated very, very frequently, maybe even once a day. And with this kind of data, coupled with the advances that we've seen in machine learning, now it's finally possible to really get a better understanding of agricultural systems, what people produce, how productive the crops are all over the world. And so we've looked at a number of problems in this space. The first one, perhaps the simplest one that one can think of, is to try to classify different kinds of crops. So given a patch, an image from a particular location, the question is, can we classify that input image into one of several kinds of crops? And this is kind of like a classic computer vision problem, where it's just image classification. And we know that there's been a lot of progress in this kind of tasks using deep learning and convolutional neural networks. One of the challenges of applying these kind of technologies in this space is that they work pretty well in developed countries, in the US, Europe, but if we want to apply them in developing countries, then things become much harder. And one of the reasons is that although we get a lot of images, a lot of inputs, labels are very, very scarce. And also the systems that we need to, the kind of agricultural systems in developing countries are quite different. Fields are much smaller. People tend to grow multiple kinds of crops in the same field. And so this creates many challenges that makes crop type detection much harder when we try to apply it in developing countries where these systems would be most useful. What can we do to try to make these systems better and more data efficient? One thing we did was to take inspirations from NLP, where people have been very successful using representations of words or sentences that have been obtained using some kind of unsupervised pre-training approach, like the word-to-vec model that is able to map words to vectors that kind of like capture the semantic meaning of the words. And these models can be trained in an unsupervised way using large collections of unlabeled data. And so what we did was to extend this approach to geospatial data with an approach that we call tile-to-vec. And the basic idea behind tile-to-vec is exploiting the first law of geography, which says that everything is related to everything else, but near things are more related than distant things. And so we can take advantage of this kind of prior, this kind of intuition, to try to come up with a learning objective, an unsupervised learning approach that will try to find a way to map images corresponding to locations that are close to each other geographically to a vector space representation that are also closer to each other. Now the process works as follows. We start by sampling an anchor tile somewhere at random. We then define a spatial neighborhood around the anchor tile. We sample a neighbor tile within the spatial neighborhood. Then we sample a distant tile outside this neighborhood. Given these three sample tiles, the idea is that because the anchor and the neighbor tile are close to each other geographically or spatially, then they are more likely to have a similar meaning than the anchor and the distant tile. And so we can use these triplets and to train a convolutional neural network that will try to map patches, images, to vector representations, to embeddings that are more semantically meaningful. And the way we can do it is by taking advantage of this intuition that the embedding of the anchor and the neighbor tile should be closer to each other than the embedding of the anchor and the distant tile. So what we can do is we can optimize the weights of the convolutional neural network to try to achieve this objective as well as we can. I'm not defining it mathematically, but it's kind of like a standard triplet loss. And the advantage here, of course, is that just like in NLP, we don't need labels to do this. We can just use unlabeled data for which we have access to essentially as much as we want, and just sample as many triplets as we want, and we can optimize this objective. And the hope is that by doing this kind of unsupervised pre-training, the convolutional neural network will learn how to map images to vector representations that are semantically meaningful and useful for many downstream classification and regression tasks. And we've applied tile-to-vec to a number of tasks. Here I'm showing you the results when we look at the crop classification problem that we talked about before. We evaluated the performance as a function of the amount of labeled data available on the x-axis. And of course, higher accuracy is better. And we compare standard supervised architectures that have been very successful in computer vision. And we look at what is the performance as we increase the amount of labeled data that is available. And we see that although they tend to perform reasonably well when the amount of labels is fairly scarce, on the order of a few hundred or a few thousand, which is kind of like the typical scenario in in developing countries, the performance is actually pretty low. On the other hand, if we look at the orange curve, which is the Tal-to-Vec approach, we see that the performance is already quite good, even in the small label data regime. And we need up to something like 50,000 labels for supervised models to catch up with the performance of Tal-to-Vec. And so Tal-to-Vec is actually a pretty useful kind of representation learning technique that we've applied to this kind of problem, but to also a variety of other classification or regression problems based on satellite images. So if you have these kind of problems, I encourage you to take a look and try our Tal-to-Vec approach. We've also looked at the problem of field delineation. So it's more like a segmentation problem where we try to identify the boundaries of the fields. I'm not going to talk much about this because we have a workshop we have a paper in this workshop, so I encourage you to take a look at that. Instead, I want to talk a bit about yield prediction, because this is really one of the key inputs that is needed when we think about decision making in the space of food security. And so we would like, after we are able to identify where the fields are and what kind of crops people grow, we would also like to figure out from space, from satellite images, how much food is actually being produced in a field, in any particular field. And this is what we've looked at, again, using remote sensing data and machine learning. Here, instead of looking at single images, we typically need to look at sequences of images. Think of them as a video, because we need to understand the health of the vegetation during the growing season. And it turns out that using a combination of deep learning, so convolutional neural networks, and some ideas from spatial statistics, like Gaussian processes, it's possible to do quite well. We've trained this kind of models in the US, looking at major crops like maize and soybean, and we've been able to get extremely high accuracy in making predictions about how much crops will be produced in different counties and in different fields. Again, I don't have time to go too much into the details of how this works, but the key idea is really to combine a traditional convolutional neural network that will take the images or the videos as inputs for each location. And the idea is that we want to like to, all these predictions that we're making over space and time, they are not independent. They're obviously correlated. And so we would like to tie them and take advantage of this prior that we have. And one way to do it is to enforce spatial correlation using a Gaussian process layer, which is, you can think of another neural network layer that is fully trainable in an end-to-end fashion, but where we use a spatial kernel that is basically enforcing the fact that nearby locations are more likely to have similar yields than if locations are farther away from each other. And the other nice thing about using a Gaussian process is that it allows us to quantify uncertainty in the predictions. So given a new field for which we don't have ground truth values, we can take the corresponding image, feed it into the neural network, extract the right features, feed them into the Gaussian process, and we don't only get a prediction for the estimated yield, but we also get a notion of uncertainty, basically based on how similar and how close this location is to other fields that we have in the training set. The model will associate a notion of uncertainty about how confident the prediction is. And this is useful as an input to decision making, but it can also be used in a semi-supervised learning approach, because we know that's generally a good idea in classification to try to have an unlabeled data point, and we have some notion of uncertainty of our prediction for that unlabeled data point. What we can do is we can try to minimize this notion of uncertainty. It's often done using entropy in the context of classification problems, and that will encourage the decision boundary to kind of like shift away from data dense regions, which is typically a good prior, a good inductive bias for many learning problems. And indeed, we've shown that this kind of approach is quite helpful across a range of regression problems, including yield forecasting. And yeah, as I mentioned, this approach works quite well. We've applied it both in the US, but also in many developing countries and also in South America. And what we can do is we can identify all fields in a particular region with a particular kind of crop. And we can figure out how productive these fields are. And we can come up with estimates, let's say for a whole country or for states within a country, or we can zoom in and understand the variation in food production levels, let's say at the district level, but we can really zoom in all the way to individual fields, and we can figure out how productive these fields have been over the years, and to some extent we can also produce forecasts about how much maize will be produced in a particular field in a particular year. And of course, these inputs are potentially very useful for decision making, and we're hoping that they will lead to better decisions and overall to an improved situation on the ground. So this concludes my talk. I hope I convinced you that there is a lot of potential for using AI and machine learning to address these big societal problems like food insecurity, poverty, and there's of course a lot more to be done, but I hope we can grow a community of people interested in working on these sort of problems, because the potential impact is indeed extremely large. So thank you for your attention, and I'm happy to take questions.